This is the 25th video in a series that I'm making to support a course in elementary number theory. And we just got done talking about quadratic residues and quadratic reciprocity. And now we want to actually solve the quadratic congruences, or decide when they're easy to solve and when they are hard to solve. But before we start proving some propositions related to that, let's recall a couple of things. First is the Legendre symbol, which we denote by A by P. And so recall that the Legendre symbol has an output of 1 if there exists an x, which is an integer, such that x squared is congruent to A mod P. So in other words, A is a perfect square mod P. I've left out a little bit of a detail here about P not dividing A, but I'll let you guys review those videos if you need to. Okay, another thing that we know is that using quadratic reciprocity, which is a very beautiful and powerful result, it is fairly easy or fairly straightforward to calculate the value of the Legendre symbol. So that means it's fairly easy to decide if some congruence like this has a solution, but actually solving this type of congruence is often very hard. There are some special cases where it's not so hard, as we'll see, but there is one special type of prime where this is like sort of unreasonable to describe at a course of this level. Okay, so let's look at the following proposition. So if P is congruent to 3 mod 4, so in other words, it's of the form 4k plus 3, and we set x equal to plus minus a to the p plus 1 over 4, then x squared is congruent to a mod p. So in other words, this value of x solves the congruence. So in other words, we have a specific solution for this congruence. Now you might be worried here because we have something that looks like a rational number in the exponent, but we're okay because if p is congruent to 3 mod 4, then p plus 1 is a multiple of 4, so we can divide by 4. Okay, great. So now let's see how the proof goes. So let's start with this underlying assumption that A is a quadratic residue. Otherwise, we can't really get off the ground. So in other words, we know A by P is equal to 1. In other words, the Legendre symbol of A and P is 1. But then also, by something called Euler's criterion, which we proved in a previous video, there's another way to calculate the Legendre symbol, and that is as follows. We know A by P is congruent to A to the P minus 1 over 2 modulo P. Okay, great. So now putting all of this together, we see that A to the P minus 1 over 2 is congruent to 1 mod P. Again, because A by P is 1, and by Euler's criterion, A by P is congruent to this. And those are all of the facts that we need to build up, and now we can just compute the square of this object. So let's go ahead and set x equal to plus minus A to the P plus 1 over 4, and notice that means x squared is A to the P plus 1 over 4 quantity squared. Notice the minus sign, which is potentially there, squares out. But that gives us A to the P plus 1 over 2. But then let's notice that A to the P plus 1 over 2 is A to the P minus 1 over 2 plus 1, like that. But now separating that out, that is A to the P minus 1 over 2 times A. But then by this thing that we just finished arguing, we know this A to the P minus 1 over 2 is congruent to 1 mod P, which means this whole thing is congruent to A mod P. So in fact, this can be used to construct a solution to this type of congruence in the case of these types of primes. Okay, let's maybe get rid of the proof and we'll do an example of this in action. Okay, now that we've got a technique for constructing solutions to this type of quadratic congruence, let's look at an example highlighting this type of solution. So we're going to solve the congruence x squared is congruent to 18 mod 23. Before we get going, let's calculate the Legendre symbol to make sure there's a solution in the first place. Obviously, this would not be a good example of this proposition if there was no solution, but we might as well take the opportunity to practice calculating the Legendre symbol with quadratic reciprocity. So that means we want to calculate 18 by 23, this Legendre symbol. But notice that 18 is the same thing as 2 times 9. So we can rewrite this as 3 squared by 23 times 2 by 23. Because whenever you can factor this top part of the Legendre symbol, you can split it up into 2 Legendre symbols. So we proved that previously. Next, 3 squared is already a perfect square, so we don't even have to think about this. Remember, the Legendre symbol is a question. Are you a perfect square mod 23? 3 squared is obviously a perfect square. So that means all we need to worry about is 2 by 23, because the output of this will be 1. Okay, but now let's notice that 2 by 23 is most definitely equal to 1 because we know that 23 is congruent to minus 1 mod 8. And 2 is a perfect square mod p if and only if p is congruent to plus or minus 1 mod 8. So that's a little fact that you should maybe keep in the back of your mind while you're working with these quadratic residues. Okay, great. So now we know there's a solution from this. Now let's build the solution using the output of this proposition. So we know the solutions are the following. So we've got plus minus 18 to the p plus 1 over 4. So that'll be 23 plus 1 over 4. In other words, it'll be 6. So that means we need to calculate plus minus 18 to the 6. Those are guaranteed to be solutions to this congruence by the proof that we just had. Okay, well, let's just go ahead and calculate 18 to the 6, and we'll get minus 18 to the 6 for free. So let's notice that 18 to the 6 is the same thing as 2 to the 6 times 3 to the 12. That's because it's 3 squared to the 6th power. But now let's notice that that is equal to 8 times 2 cubed times 27 to the 4th. That's because 12 is equal to 3 times 4th. So that's a nice simplification that we can do. Next, we see that 27 is 4 mod 23. So we can replace all of those with 4, leaving us with 8 times 2 cubed times 4 to the 4th power. But let's notice that 4 to the 4th power is 2 to the 8th power. So we have 8 times 2 to the 11. And then I'll let you guys check what 2 to the 11 is mod 23. You can do that with successive squaring or something like that. But in the end, this is all congruent to 8 mod 23. So that means our solutions are plus minus 8, but minus 8 is the same thing as 15. So our two solutions are 8 and 15. Okay, so let's maybe get rid of this and we'll look at a similar proposition for other types of primes. Okay, so our next proposition has to do with primes of the form 8k plus 5. In other words, they are congruent to 5 mod 8. Then x squared congruent to a mod p has one of these as a solution. So it's either a to the p plus 3 over 8, or it's 2 to the p minus 1 over 4 times a to the p plus 3 over 8. Okay, so let's maybe see how we can do this. We're going to start with the same kind of thing that we did on the last proof, and that is with Euler's criterion. So let's notice that by Euler, we know a couple of different things. We know we don't know this by Euler. We know this by the fact that this has a solution in the first place. A by p is equal to 1. And then we also know that that is congruent to a to the p minus 1 over 2 mod p. That's by Euler's criterion. Okay, another thing that we know is based off the fact that P is 8k plus 5. So let's write that. P is 8k plus 5 because it's 5 mod 8. That means that P minus 1 over 2 has a special form. And what is that form? That is 4k plus 2. Okay, so now putting this value for P minus 1 over 2 into this congruence up here, we see that a to the 4k plus 2 is congruent to 1 mod P. That may not seem too helpful, but that also tells us that a to the 2k plus 1 squared is congruent to 1 mod P. But now a to the 2k plus 1 is a solution to the congruence x squared congruent to 1 mod P. But because of the type of prime we have, that tells us that a to the 2k plus 1 is congruent to plus minus 1 mod P. But then that clearly splits into two cases. That splits into the case when a to the 2k plus 2 is congruent to a mod P. I'll just multiply both sides of this congruence by a, or a to the 2k plus 2 is congruent to negative a modulo P. Now we need to look at each of those cases on their own, but we're running out of room, so let's bring that up and we'll do just that. So in the last board, we ended up with two cases. Let's start with this positive case. In other words, we have a to the 2k plus 2 is congruent to plus a mod P. But let's notice that that means that a to the k plus 1 squared is congruent to a modulo P. Well, so we've got a solution to this congruence where x is equal to a to the k plus 1. May not seem like we've solved it yet, but we can easily calculate that k plus 1 is equal to p plus 3 over 8. And that is, again, built off of our kind of original assumption that p was equal to 8k plus 5. That's the translation between p and k. But now just slamming this into here, we see that a to the p plus 3 over 8 squared is congruent to a mod P. So in other words, this guy is a solution to our congruence. Okay, so now let's do our second case. So since I called this first case, case plus, let's call the second case, case minus. So here we have a to the 2k plus 2 is congruent to negative a modulo P. And this case is a little bit trickier, but not too bad if you recall some of the facts that we've seen in the past. So first of all, we know the Legendre symbol 2 by p is equal to negative 1. In other words, 2 is not a quadratic residue mod p if p is of this form. But then by Euler's criterion, we know that this is congruent to 2 to the p minus 1 over 2 mod p. So we're using Euler's criterion all over the place here. But now we're pretty much good to go, because if we take this object right here, 2 to the p minus 1 over 4 times a to the p plus 3 over 8 and square it, we'll get 2 to the p minus 1 over 2 from pulling the square here. And then here we'll get a to the p plus 3 over 8 squared. But that's exactly a to the 2k plus 2, and that is negative a. But this guy right here is negative 1, which we discovered by Euler's criterion over there. So the negative 1 and the negative a cancel out the sign, leaving us with a mod p. So in other words, in this case, the solution is of this form. Okay, so let's maybe do what we did with the last proposition and look at an example of this situation. Now let's look at an example of this proposition in action. So we'll solve the congruence x squared is congruent to 20 mod 61. Let's just notice it really quickly that 61 is congruent to 5 mod 8. So it's 3 less than 64, which means it's negative 3 mod 8, but that's the same thing as 5 mod 8. So again, we'll take the opportunity to practice calculating the Legendre symbol using quadratic reciprocity just to make sure there's a solution in the first place. So we've got 20 by 61 is the same thing as 4 by 61 times 5 by 61, because we can factor this top part into two pieces like this. Okay, next, we know that 4 is a perfect square over the integers, which means it's like obviously a perfect square mod any prime. So we know the Legendre symbol here will give us the number 1. So now we just have to calculate this Legendre symbol 5 by 61. The 5 is an odd prime, which is nice because now we can flip this thing. And we flip it with either a plus or a minus, depending on the residue of these two mod 4. So let's notice that when we flip it, we get 61 by 5. Do we need a plus or a minus? Well, in fact, we need a plus because 5 is congruent to 1 mod 4. And we know if at least one of them is congruent to 1 mod 4, you can flip these with no problem at all. Okay, but next we see that 61 by 5, well, we can reduce that top part, mod 5, leaving us with 1 by 5. But 1 is clearly a perfect square, so we get 1 out of this. So in other words, we've just shown that this thing has a solution. Now we'll use our proposition to construct a solution. So we'll first try this one right here. And if this doesn't work, we'll try this one right here. Okay. So let's see what we have to do. We need to calculate a to the p plus 3 over 8. So here a is 20, and then p plus 3 is 64, divided by 8 is 8. So we've reduced lots of things like this, mod all sorts of different numbers throughout this course. So I'm not going to do the details here. I'll just tell you that this is congruent to 9 modulo 61. But now we're not guaranteed that this is a solution. Look, our proposition tells you that this guy is a solution or this guy is a solution. Well, we can check by doing 9 squared, noticing we get 81, which is most definitely congruent to 20 mod 61. And then after looking at this, it's pretty obvious that 9 should be a solution, but I think it's nice to go through the details just to see this proposition working. Okay, so I'm going to finish this video off with a little discussion on what we know, how we can find solutions, and which types of primes we do not know how to find solutions to. Now we're going to summarize the results that we've seen in this video. So starting with even primes, well, there's really only one even prime, and that is the number 2. So there's only one quadratic residue, and that is the number 1, but 0 is also a perfect square mod 2. So here you can think of as everything being a square. There's really no worries. Now, what happens if you have an odd prime? Well, if you have an odd prime, you're in 2 cases. You're either congruent to 1 mod 4 or you are congruent to 3 mod 4. The first proposition we proved was a construction for a solution in the case when we are 3 mod 4, so we're good in that case. Now, if you're 1 mod 4, that's going to split into 2 cases. You are either 1 mod 8 or you are 5 mod 8. So the second proposition that we proved gave us some sort of construction in the case of 5 mod 8. It wasn't quite as nice as in the case of 3 mod 4 because it had this either or statement in it, but it still gave us a solution. Now, in this other case down here of p congruent to 1 mod 8, unfortunately, there is no easy solution. Let's think about why that is the case. So in our p congruent to 5 mod 8 case, we were able to hack the bad case. So in other words, that case where you had a to the 2k plus 2 and it was congruent to negative a mod p, using the fact that 2 is a quadratic non-residue mod p when p is 5 mod 8. In other words, this Legendre symbol, 2 by p, is negative 1. Well, the problem occurs because if p is congruent to 1 mod 8, quadratic non-residues are not systematic. So this is systematically a quadratic non-residue if p is congruent to 5 mod 8, but there's no real systematic quadratic non-residue to use as a tool if p is congruent to 1 mod 8. Okay, so let's finish this video off with some warm-up problems to try. Okay, here's a couple of quick warm-up problems based on the techniques in the video. So solve the following congruences, not by guess and check, but by using the propositions from this video, just for practice to get an idea for how they work. So the first is x squared is congruent to 12 mod 15. The second is x squared is congruent to 55 mod 77. Then if you feel like you need extra practice, maybe you could like write some of your own congruences and solve them. So maybe leave some that you find interesting in the comments, and that's a good place to stop.